Hi, everyone. Ray Smith here.
Priya,
Welcome.
Donti.
Yes, hi. Welcome to our session, the theme, Computational Tools for Sustainability. And this session, Advancements in Sustainability Decision Support Tools. So we're all in virtual room 1 right now. As usual, I think things don't usually start right on time. 5:30 is the suggested start time, but I would imagine that people will be coming in the room, as in here in these first few minutes. I guess I could take a moment to introduce myself. My name again is Ray Smith. I have been working at the U.S. Environmental Protection Agency for the last 22 years. After getting my PhD in chemical engineering. I'm working on projects like predicting or estimating releases from chemical processes that are useful for exposure assessments and of course life cycle assessment. And I'm also doing projects like looking at plastic flows in the United States and the different kinds of recycling steps that are involved in that. So those are a couple projects that I'm interested in or doing currently. So Priya, do you want to introduce yourself?
Sure. Hey, everyone. So I'm Priya Donti. I'm a PhD student at Carnegie Mellon in computer science and public policy. And my work focuses on the intersection of machine learning and electric power systems. So specifically, I think a lot about how do we better forecast renewables, more quickly optimize power systems in a way that is both data driven, actually adapts to the situation of the power system as we see it, while also respecting various sorts of physics and hard constraints. So my work primarily focuses on incorporating the physics of the electric power grid into machine learning methods.
Very good. So I've seen that a few more people have come in here into the room as we've been talking. So again, I'm Ray Smith. We've just gone through our introductions. We haven't started with the first speaker yet. We were going to give people just a few minutes here to come into the room. Do you think of any other item that we need to cover before we get going?
No, I mean, so I think at the bottom of the of your panel, you'll see sort of a text chat option, which will open up a group chat for you. So if you have questions during the presentation, do feel free to drop them into the chat, and we'll make sure that they get asked. We'll be doing a kind of a presentation from each speaker, followed by a short Q&A session. And at the end, I believe we'll have time to sort of bring all the speakers back onto stage and do a larger Q&A. So if we don't get to your questions in the interim, we'll get to them at the end. So please stick around and enjoy.
Yes, quite right. So the plan is for 15 minutes for the speaker and then 3 minutes for Q&A immediately. And then at the end, hopefully we'll have a lot of interesting discussion and we have time for that at the end as well. So I think we've given everyone a few minutes now, so we could start with the first speaker. Let me give him an introduction. Got to open up my file here. Okay. So Noah Sandoval is a PhD student in the Advanced Energy Systems program, which is a collaboration between Colorado School of Mines and the National Renewable Energy Laboratory. He has degrees in engineering science and Spanish from the Colorado State University and has 6 years of secondary education science teaching experience. His research is focused on incorporating energy justice metrics into energy modeling in order to work towards a more just and equitable energy system. And we're looking forward to hearing what Noah has to say. So, Noah?
Hello, how are you all?
Great, thank you.
Let's get screen share. Awesome, can you all see this?
Yes.
Yes.
Okay. Again, my name is Noah Sandoval, and today I'm going to present to you an evaluation framework that myself and the other people on this slide have been developing. And so just to kind of start, when I first started research, my first task was to look into the best practices in energy modeling and scenario development. And what I noticed in some of these large and major energy models was a lot of their scenarios were lacking complexity. They were very one-dimensional. They just weren't very rich kind of pictures of the future. And when I looked into the documentation even further, there wasn't a lot of information about how these scenarios were developed. So I took a step back and I looked at the literature and kind of trying to understand what is out there for scenario development. And on one hand, there's a lot of theoretical ideas about what a scenario should look like, its purpose, its structure. And then a couple steps forward, there's just critiques about models or about the field in general. And there's not a lot of kind of in the intermediate steps to get there on how to develop high quality scenarios. And what I really realized was there's a mismatch between what the theory says about scenario development and then what we are actually doing in practice. And then there's two big things that I realized that a lot of scenarios were missing. First of all, a lot of scenarios don't have futures which are internally consistent. And what I mean by that is that these futures aren't necessarily plausible or reliable pictures of what the future could hold. They're really futures that may not even be possible, which is a huge issue. There's already a lot of uncertainty in the energy modeling field, and we don't want to add even more uncertainty to that. So we want our scenarios to be internally consistent. Likewise, it seemed to be the field seemed to be missing a lot of diversity. And when I talk about diversity today, I'm going to talk about it in two senses. The first sense being diversity within a single scenario, and that scenario represents this very intricate and complex energy system. And then I also mean diversity in the terms of diversity in a set of scenarios. Do we have a wide range of scenarios where we can really compare and contrast their results and really get meaningful analysis out of that? So those are the two things that I'm going to focus on today: internal consistency and diversity. And so with this in mind, why would we develop an evaluation framework? First of all, like I said, there are definitely some gaps in the current literature in that there's not an easy way to quickly analyze different energy models and look at and give targeted feedback to how these models can improve. Likewise, there's not a ton of information or a ton of literature comparing energy models side by side. And if we can do that, we can really quickly identify trends and gaps in the literature. Furthermore, we realize that in developing this framework, it really, fills that gap of that intermediate step of getting developed and robust scenarios into the field. And I think furthermore, it can really just further the discussion on what is scenario quality and how can we create really high quality, good scenarios. So in creating this evaluation framework, we're going to stick to these two big buckets of internal consistency and diversity. Starting with internal consistency, this was kind of broken down into two smaller evaluations: access and the development process. So as I go through these different evaluations, we can see this key and kind of on the right side where we have best acceptable and unacceptable practices. If you can't see the colors there, top is best, bottom is unacceptable. So in terms of access, we're asking, is this documentation accessible? Is it available to the public? Is it easy to access and easy to find that information? And then also, we want it to be understandable to the largest group of people. And so we want a really low technical knowledge requirement for that best practice. Next, we want to ask, is there a rigorous development process? So firstly, looking at the narrative, is there a really detailed and thought out and intentional narrative that the modelers have created to represent not only the first, but the second and third order effects of the changes that these different scenarios could have on possible futures? From there, we want to look at the data, which is taking these qualitative narratives and translating them into the variables that we'll input into our quantitative models. And then lastly, we want to make sure that stakeholders are involved at every single level from a variety of different fields. So with those two, we can answer the question, are the futures presented in these scenarios possible? And from here, if we say yes, they are possible, we're going to ask, okay, are they diverse? And here we're going to look at variable diversity and scenario diversity. The key is a little different here, you'll notice. We don't have the colors. Instead, we're looking for diversity. So our goal is to have as many of these different classifications as possible. And we first want to focus in on each individual scenario and ask, is it a rich and complex future that's being represented? So we want to look at variable type, and how we're typing these is, does that variable primarily impact the supply, the demand side, or kind of a mix, an indeterminate mix of the two? Likewise, we want to look at the control over which we as stakeholders have the control we have over that variable. Internally controlled variables are something we have complete control over, versus external is something where we don't have, we have little to no control over. From here, we can then look at the set of scenarios as a whole, and look at the outlook, whether it's forecasting, it's forward-looking and simulation-based, or whether it's backcasting, where we start with a final predetermined state and then optimize towards that. And then we're also going to look at scenario progression, whether we have a trend-based scenario that just extrapolates off historical data, or a peripheral-based scenario that has some sort of disruption that cannot be predicted by historical data. So if we answer each of those four kind of questions in sequence, we can say that our scenario meets that analysis criteria. And if not, it's really easy to identify what went wrong and how to improve that. So for our case studies, we're going to look at 5 different major energy models. We're first going to look at the annual energy outlook put out by the EIA, the world energy outlook put out by the IEA. We're going to look at a journal article which used the Scout tool, which is a tool developed by the Department of Energy. We're also going to look at the LA 100 study, which was recently published by the National Renewable Energies Lab, which uses a variety of in-house models. And then we're going to look at the shared socioeconomic pathways, which is developed by the Intergovernmental Panel on Climate Change for their various integrated assessment models. So here's our first kind of synthesis of results, and I know this table can be pretty big and overwhelming, so I'm going to first by just kind of breaking down the scenario just to kind of explain it. So over here on this left side, we have all the different scenarios, and the one with the asterisk is our reference or baseline scenarios. We have each of the 4 evaluations, and then for our variable diversity evaluation, each plus sign represents a variable which was used to differentiate that scenario from the baseline scenario. So we want more pluses in more places on this field. And then furthermore, we kind of have an analysis or a synthesis of each one of these evaluations. So looking at the annual energy outlook, we have low access requirements, but unfortunately we have a really weak development process where only the reference scenario is really given any notice. And then looking at the amount of variables and their diversity, we're really lacking and missing a lot of diversity here in our variables. And then we have no mix in either our scenario outlook or progression. So we've got a lot of work to do here. Moving forward with the world energy outlook, again, low access requirements, slightly better development process. We've got more variables, more types of variables, more control levels. We do have a mix of scenario outlook, but again, no mix in our progression scenarios. Looking at the Scout tool, in this article, there was a bunch of different scenarios which were used. Other than high technical knowledge requirements, we've got a pretty good access, a much stronger development process, only kind of lacking in the narrative complexity. And then again, we're covering a lot more ground here with the types and control levels of the variables included, but we're still missing some diversity here. There's no mix in scenario outlook, but we do have some peripheral-based scenarios. Moving on to the LA 100 study, similar access requirements, a very strong development process across the board. We have even more variables, and we're only missing our supply type variables. But again, over here, there's no mix in scenario outlook or progression. And then finally, the shared socioeconomic pathways, similar access requirements, another strong development process, and we have lots of variables over all variable types. Really, the only thing missing here is no internal variables. But again, no mix of scenario diversity. So I know I ran through that really quickly because I really want to focus more so on the trends and kind of the findings here. And so firstly, I want to say that in general, the access requirements were pretty low. And that makes sense because these are some big energy models. They're well known. They're used to calibrate models. And so the access really wasn't an issue. But I think if we're looking at the field in general, access may become an issue down the line. So moving on, we're then going to look at the development process and ask, is this rigorous? And for 3 out of our 5 models, we're going to give the thumbs up and say, yes, absolutely. Unfortunately, 2 of our models did not have a rigorous development process, and so they could not answer yes to the question, is this future even possible? So a couple of things here. It could be just an issue of communication, and that the communication of the development process really wasn't great, and we can improve there. If not, then there's a bigger issue of really having to reevaluate that development process. But I do want to take a second to think about this and say 2 out of the 5 of our scenarios were missing, I think, this absolutely fundamental question of, is this future even possible? And I really want to think if 2 of these major energy models were missing this, how many other models across the field are missing this? And really giving results that are really unbased, and really it would be difficult to actually take those results at face value. So that's kind of my first note to you all. Looking at diversity and specifically at the diversity within the scenarios, most of our scenarios only featured 1 variable type. And so these scenarios are very one-dimensional. They don't take into account the different intricacies and dynamics within our energy system. And so they're not very rich futures. And I think that's a really big issue. And then secondly, a lot of our scenarios didn't feature variables with internal control. And so they didn't feature variables where our stakeholders had agency in how the future developed. And it is absolutely important to model those things outside of our control, to understand the implications of kind of where we're going and what's going to happen in the future. But likewise, it is just as important to model scenarios in which we have agency to change trends and to redirect our trajectory in the future. And so that's my next kind of note to the field, is we really need to increase the complexity of our scenarios, but we also I want that to see more internal based variables used in our scenarios. And then lastly, we're going to look at the sets of scenarios as a whole. We only had 1 backcasting scenario. And these backcasting scenarios are really important in terms of learning how we can achieve goals and learning the pathways to achieving those goals. They're less deterministic than our forward-thinking ones, and they really they offer alternative pathways to get to some of these zero emissions kind of targets that we have. And then also, only 2 scenarios had peripheral-based progression. And if you could, predict when certain disruptions were going to happen, you probably wouldn't be in this room. You'd probably be very rich, and there would be no need to do energy modeling. And it seems very difficult. Like, how can I predict when a disruption is going to happen? But rather than kind of back away from that, I really think we should lean into this and really understand the sensitivities around different disruptions in different sectors at different magnitudes, at different time scales. So maybe we won't be able to anticipate a disruption, but we'll be able to best react when those disruptions do happen or we start seeing them. So I would love to see more peripheral-based progressions and more backcasting type scenarios. So in conclusion, so what? If we get this wrong, what happens? Well, first of all, we're potentially creating unrealistic views of the future, and this could lead to inappropriate actions. We could miss opportunities. We could have a misunderstanding of impacts that are happening now and in the future, and that means a less reliable and resilient energy system. And that could have environmental, economic, political, or social ramifications. So we really want to avoid that. So looking forward, I think there's a ton of value in our evaluation framework. It provides quick, actionable, and targeted feedback. We can compare any type of energy model really quickly. We can, in highlighting trends and gaps in the field. And then finally, for future work, I'd love to apply this to more energy models. It can be used as a guide for scenario development. And this framework is very simple. It can be easily expanded and adapted as other needs are identified and the issues of scenario quality progress. So with that, I'd like to thank you all. And I'd love to hear any questions and comments that you may have.
Thank you, Noah. So thanks for your presentation. We appreciate it. Very good. While we're waiting for people to type in some questions, I thought I'd maybe start with one that occurred to me. And that is there a chance that these different, I know we're calling the five different systems that you went over. I'll call them systems. The five different systems that you looked over, do you think of them as having different purposes, and therefore that's why you saw differences between them? Or is there some other basic reason why they were so different?
Yeah, absolutely. We have big, integrated assessment models that use the shared socioeconomic pathways. And so, it's pretty clear that those would have a lot of diversity and have a lot of, check a lot of these boxes. And then you have something like Scout, which is a building energy, bottom-up building energy model. And so that's much more specific. And so, yeah, absolutely. We're going to see the different purposes there. And I think we used different models just to show that this framework could be applicable to a variety of different models, and more so to understand the trends across a lot of these different things, a lot of these different models, and just understand what are we projecting, regardless of the model, and what are we not.
Very good. Priya, do you have something or?
I think we have one in the chat, actually.
Okay.
So we have a question from Michael Craig, who asks, how do you define possible? In some sense, this may seem a little circular in that, models help us understand possible, but then the models require scenario runs, and possible is a really flexible term. So how do you sort of contend with this in your work?
Yeah, of course. That was a tricky wording thing that my advisors and I kind of constantly went back and forth on. And I think when we talk about possible for internal consistency, we're looking at, do these scenarios represent futures which are multidimensional and interesting? And so if we change something like high economic growth, and that's the only thing we change, is that really a realistic version of the future? Isn't high economic growth going to have other effects within our energy system? And so I think that's what we're looking at in terms of, is it possible? And really thinking about the complexity and the thought and intention behind these scenarios, and say, okay, well, if we have high economic growth, what else is going to happen? What are the different impacts? And so, yeah, we definitely have some gray area there, but that was kind of the intent with, the word possible. Does that answer your question? I can't see. Well,
it was from Michael Craig, so he could send us a text maybe or a message and let us know. But in the meantime, we can move on to a question from Rebecca Haynes. Rebecca asks, increasing diversity in model scenarios can absolutely provide a more realistic picture of the future, but it will also increase uncertainty in model results and potentially impede decision-making. So have you thought about this trade-off and how to mitigate?
I don't think specifically. I think one of the initial goals of this project was really that communication between modelers and then stakeholders and decision makers, and really the goal to communicate what these scenarios are actually doing, and that was kind of the genesis of this, and really realizing that there isn't a great communication there. And so I think it definitely could by adding uncertainty, but I think the increased communication of, okay, why did we choose let's say now an electrification, and what were the results, or what were the implications of that? I think there are trade-offs, but if you have that discussion of why this scenario, that leads to just a better understanding overall. And so, yeah, of course there's uncertainty, but our goal is just to improve communication about the purposes of these scenarios and how realistic these scenarios are.
So we do have one more question before moving on, and it happens to be from our next speaker. So Amanda Farthing asks, did Noah and the team compare the results of their matrix to the historical accuracy of the models? And then parentheses, she puts, for those models that projected results several years ago.
So no, this is less so about the results and more about the development process. So there are lots and lots of analyses that have already been done that look at how accurate these models are, and what we're doing is not necessarily focused on the back end of and the results of those scenarios, but rather how do we get to those scenarios in the first place, and how do those get input into our models.
Okay. Very good. Well, thank you, Noah. I hope that we have a rich discussion at the end, and we appreciate your presentation and the Q&A there. So our next speaker, let me quickly, is Amanda Farthing. So Amanda is a recent graduate from the University of Michigan, where she obtained dual master's degrees in sustainable systems and mechanical engineering. Today, she will be presenting her master's thesis work. Following graduation, Amanda joined the modeling and analysis group at the National Renewable Energy Laboratory, where she helps develop and apply REopt Light, a techno-economic optimization model for on-site renewable technologies, to help stakeholders meet their energy and emission goals. So Amanda, there's Amanda. Welcome, and thank you for being here and presenting to our group, and we look forward to your presentation.
Hi, thank you so much.
I assume you'll be sharing your screen.
Yes, I will. Great. Are you able to see my screen?
Yes.
Okay, wonderful. Hello, everyone. I am very excited to be talking about the results of my thesis work, for which I integrated climate, health, and resilience into the valuation of solar and storage projects. And this work was advised by Professors Michael Craig and Tony Reams at the University of Michigan. So just as a bit of context, as you all likely know, in the US, grid-connected distributed solar has been exponentially increasing, and the percentage of these systems that also have behind-the-meter storage is increasing and is expected to continue to grow. So local governments are some of the entities that are looking to pursue these on-site solar and storage projects, and oftentimes to meet climate targets or renewable energy targets. And so this is a general trend that we're seeing, is entities pursuing solar and storage, not just for bill savings, but also for things like resilience to grid outages, as well as to meet climate goals, oftentimes like the city of Des Moines looking more granularly at those climate goals, so making 24/7 clean electricity pledges, and also in consideration of the public health impacts of the electricity that their buildings are using. So focusing on local governments, given their portfolio of buildings and their priorities, they must decide where and how much PV and storage to deploy, as well as the operational strategy or the battery dispatch strategy for those systems. So this leads to my research question, which is, what is the impact of including resilience, climate, and health, costs and benefits on the cost-optimal sizing and economic returns of on-site solar and storage projects? So as a brief overview of my methods, this research expands upon the typical cost-optimal approach to evaluating these investments, which says I will choose the solar and battery size, as well as the battery dispatch strategy that minimizes the life cycle costs of the system, considering capital costs, operations and maintenance costs, and electricity bill costs. And you would typically compare this life cycle cost to your business as usual life cycle costs to see if you should make the investment. So the expanded approach additionally considers microgrid construction costs, the cost of incurring a grid outage, as well as climate costs and public health costs of grid purchased electricity within that life cycle cost calculation. And so the tool that we used for this work is the REopt Light open source Julia package, which already incorporates the ability to evaluate bill savings as well as resilience within that model. So today I'll mostly be focusing on what I incorporated for my thesis, which was the public health and climate costs of grid purchased electricity. So just as a brief overview, both public health and climate costs are related to emissions from the grid, and these emissions costs are calculated as the marginal emissions rate, so ton of pollutant per kilowatt hour times the marginal emissions cost, or dollars per ton of that pollutant. So for climate costs, for the marginal emissions rates, we use the Cambium data set that is forward-looking, so they project what the grid will look like on the margin out into the future. It's hourly and at the balancing authority scale. And for the cost of carbon, we use the social cost of carbon from the government. And then for health costs, because marginal emissions rates for SO2 and NOx, which are the pollutants that we considered for their public health impacts, because those marginal emissions rates are not included in Cambium, we got that data from the EPA's needs database and averaged those rates by plant type and region. And the marginal health costs for SO2 and NOx we obtained from EASIER, which is a reduced form air quality model that says if for every additional ton of pollutant in a given location, what is the estimated increase in mortality in that area, and what is the associated cost? And then the outage cost, which again was already part of that model, is the maximum expected outage cost over all possible outage start times, plus the cost to upgrade your system to be islandable from the grid. So these new emissions-related parameters were incorporated into REopt Lite along with the typical considerations to output the optimal solution, which mainly consists of the cost-optimal technology mix, so the sizing of solar and storage, as well as the lifetime net present value of that investment and the dispatch strategy of the battery. So in implementing this model, we evaluated 3 building types: a hospital, school, and warehouse, primarily for their differing roles that they could serve during a grid outage. So a hospital is, of course, a critical facility. A school could serve as a community resilience hub, and a warehouse may be non-critical to remain powered. And so these differing roles correspond to differing values of lost load and the critical load percentage that you would want to keep powered during an outage. And the expected outage characteristics that we modeled were a 15-hour outage occurring at the 5% worst possible times for each building, given that building's load profile, and we assume that outage occurred annually. We modeled these 3 building types in 14 cities across the continental US, spanning 14 unique climate zones. So of course, each has a unique load profile and utility tariff structure. And then just to note, the emissions rates, as well as the marginal emissions health costs, are very different across these cities. And so that, as we'll see, will impact the results of incorporating these emissions into the objective function. So results. To illustrate these results, first I'll start with one example. So the school modeled in Chicago, and we'll take the perspective of the local government there that is asking, what is the cost optimal solar and storage system size to invest in on this school, and what returns will we see for this investment? So if you are only optimizing this system for bill savings, you actually see that it is not cost optimal to invest in solar and storage, and the net present value of the investment is 0. And just a slight asterisk, I did not model any incentives within this, so that might be one thing influencing this set of results. So again, optimizing only for bill savings means it's not cost optimal to invest. If we additionally optimize for resilience, it now becomes cost optimal to invest in a over 500 kilowatt PV system and a sizable battery. And just breaking down that 25-year net present value into buckets of cash flows, essentially, we can see that the upfront CapEx and the O&M costs for this system are over $4.5 million. The energy bill savings are relatively small compared to that upfront cost. The additional micro cost to upgrade this system to be islandable from the grid is $1.4 million, and the lifetime savings from avoided outage costs is over $7.5 million, leading to that a net present value of $1.8 million. We can also calculate the CO2 and health cost savings from avoided grid purchases, even though they were not incorporated into the objective function of this optimization. And so those come out to be $290,000 for CO2 savings and $1.5 million for health cost savings. Okay, now what if we additionally co-optimize for climate and health in addition to bill savings and resilience? The cost optimal PV size is the same because that's the maximum that can fit on the roof, and the cost optimal battery size is slightly larger. We see slightly higher CapEx and O&M costs, similar energy savings and similar energy bill savings, similar resilience results, but we see much higher CO2 and health cost savings now in the range of $700,000 for CO2 and $6.7 million for health cost savings, resulting in a net present value now of $9 million. So from the point of view of the decision maker, if you're including these externalities within your optimization and your net present value calculation, now you're looking at a $9 million net present value instead of 1.8. So we saw similar results in terms of health and climate impacts being significantly higher in that bill savings resilient climate and health optimization, or BRCH is the acronym we're using. And these benefits were dominated by health as compared to climate. So the black line here would be climate and health benefits for each individual building are equal. So you'll see most of the dots, each dot representing an individual building's results, are above that line. And health is on the y-axis and climate's on the x-axis. So these results here are for just the bill savings case. If we look at the case where we're optimizing additionally for resilience, kind of seeing similar results. And then if we look at this BRCH case, now we're seeing average health and climate benefits for an individual building over its lifetime to be on the realm of 3.4 million for health and 500,000 for climate. And so this box plot is showing aggregated results across all of the cities for each building type. So the midline there would represent the median value across all the cities for each individual building type across the 3 optimization scenarios. And in just comparing scenario BR to BRCH, we see that the net present value of these investments increases by 25% for hospitals, 124% for the schools, and by over 10,000 times for the warehouse. We also dug into the battery dispatch strategy and realized that it was significantly different for the case where you're co-optimizing for climate and health, because that battery is now responding to the emissions intensity of the grid. And in general, we saw that the batteries were utilized much more frequently and discharged to greater depths when co-optimizing for climate and health impacts. And I can show those aggregate results if anyone is interested. We also wanted to look at the climate and health return on investment as a way to kind of normalize for system size. And this is particularly interesting in comparing the bill savings and resilience, or BR case, and the bill savings, resilience, climate and health case, because those system sizes were somewhat similar. And so now we can really see the additional, the influence of that battery discharge strategy on climate and health benefits. And we can see that by region broken out here. And so you can see that in general, the climate and health return on investment increases by about 50 cents per dollar invested. And these results do vary by region given the emissions intensity of the grid, and those areas with more emissions intensive areas seeing greater benefits from those solar and storage systems. So in conclusion, co-optimizing for climate and health benefits, we saw increased cost optimal system sizes and improved system economics. The optimal operations strategy of the battery will see higher utilization of those batteries. In regions with higher emissions rates, of course, we'll see greater benefits of co-optimizing for climate and health impacts by avoiding purchasing more emissions-intensive electricity. And then just to mention, future NREL REopt work will continue to incorporate these emissions impacts. And if you're interested, you can use the web tool, which currently calculates emissions impacts without incorporating those into the objective. And you can also access the open source API. So thank you so much. I look forward to taking any questions.
Thank you, Amanda. Very good. Appreciate your presentation. So again, as with the last presentation, I'll try and start with a question. So I might have missed it, but in your presentation, I saw that outage costs were rather large. And it's one of the things that really improved the final net present value. So is that something that people are taking into account now, or is this something that people need to consider? And why, if it's not being considered now, why is that?
That's a great question. Yeah, and I didn't focus too much on that in this presentation just because it wasn't the new aspect that I incorporated, but that's a great point, and we can see from events like Texas that it would make a big difference to be considering those outage costs ahead of time as a way to spur investment in resilience. I would say this is a pretty new area that people are starting to incorporate in practice. And I found in research that, for instance, like a value of lost load, that dollar per kilowatt hour value of avoided service is something that varies widely, and there's not really a consensus that I found in the literature of what should these values really be. So that could be one barrier that people see to kind of implementing that. And then another thing would just be, do the tools exist to help people analyze that? And that's something that the group at NREL is working on.
I could imagine that any investment is essentially determined by some sort of commission that says, what rate are we going to charge our customers, or different rates for different people. So and businesses. So I guess any kind of investment needs to satisfy those customers in a way. So maybe that's part of the reason why it's difficult to justify these outage. I don't know. It's another question, really for you. And have you thought about this idea of satisfying customers? And are their willingness to pay, maybe, is a way of putting it.
Sorry, I didn't quite understand the rate aspect of your question. You're speaking of utility rates, or?
Yeah, that's what I was thinking. Yeah.
Mm-hmm.
So maybe I rambled and I don't know what I'm talking about. So we can move on to another question if you think it's just a non sequitur.
Well, I certainly think that there aren't many good financial mechanisms for people to be incorporating these into their decisions and having that justified financially. But it's also not an area that I know a ton about in practice, aside from speaking to people in local governments for this research who it was definitely not a factor in their financial decisions in terms of putting a number on that value. It was more from a resilience standpoint, but without a financial justification, essentially.
I have another question to put in there. So it was a great presentation, and I guess the question I have is about emissions factors. So you used marginal emissions factors to quantify various health, climate, etc. benefits, and of course marginal emissions factors tend to describe scenarios where you have small changes in load on the grid, but some of the situations you're looking at potentially actually correspond to large changes in load. And so I wanted to ask, did you sort of how much do you think your analysis would be affected if you had to use, average emissions factors or something else? Like to what extent was that particular assumption, do you think, influential in the results?
Yeah, we did kind of have that discussion around marginal versus average. And because we were looking at results from individual buildings, we said that is a small enough change to mean that we should be using marginal emissions factors. I think if you ran like a national scale analysis and said, now we're looking at the aggregate, maybe it would then be more appropriate to use average. And I don't know, I can't answer how much it might influence the results, just having not actually run that analysis. But of course they would be different, and probably the benefits would be smaller, the climate and health benefits, particularly as we're looking at a grid having higher and higher percentages of renewables, where the marginal emissions factor might not actually represent that degree of increase in renewables.
Yeah, absolutely. It's a really tricky issue where there isn't also, in some sense, a lot of ground truth data to validate these things. So yeah, absolutely. Thanks for sharing that.
Just a quick question. Did your health analysis, did it look at mortality only, or was also considering morbidity?
As far as I understand how the easier model works, and please, if anyone on here knows more than me, feel free to correct me. But as far as I understand, they're looking at an increase in mortality that results from the secondary formation of PM 2.5.
Okay. Yeah.
I think they may incorporate morbidity, but I'm not quite sure.
Okay.
Yeah.
It's interesting though. So hopefully people will have some questions when we reach the end of the 4 talks. And thank you again, Amanda.
Yes, thank you so much.
Very good. So we will start our move now to the next speaker, which I have not met. I may mispronounce your name, so you're going to have to come in and correct me, but I might say Yuchuan Lai. So he is a postdoctoral research associate from the Department of Civil and Environmental Engineering at Carnegie Mellon University. He received his PhD in civil and environmental engineering from Carnegie Mellon in 2020. And his research topics include engineering adaptation to climate change, statistical learning, global climate models with downscaling, and drinking water temperature and quality. So we are ready for your presentation.
Great. Thanks for the introduction, Ray.
Yes. And please pronounce your name for us.
It's Yuchuan Lai, so you're pretty close. I think
you.
you're right, actually. Just let me share my screen.
Okay. And we will look forward to your presentation. Thank you for being here.
Thank you. All right.
It's sharing.
Okay. All right.
Okay. Yep.
Hi. Good afternoon. Thank you so much for being here. So the main idea of this presentation is that we want to provide this kind of statistic time series forecasting tool to project the regional temperature and precipitation for the engineering applications. So why do engineering really care about the future temperature or precipitation? Is because that there are some large impacts from growing temperature and precipitation on the infrastructure that we engineers need to consider. I have 4 examples showing here, illustrate some kind of like growing impacts from the climate change to the infrastructure. On the left 2 graphs here is kind of illustration of the increase of temperature effects. So with the increase of temperature and temperature extremes, that leads to kind of this buckling of the railroads or the buckling of the pavement. On the right 2 graphs here kind of illustrate the idea of the changes of precipitation, how that leads to the challenges for the infrastructure. On the top right graph here, with the increase of precipitation, that leads to the increase of runoff, that equates to problems such as flash flood, or in this case, the bridge scour, that kind of affects the structural integrity of the bridges. And on the bottom right graph here is a kind of more recent event. It's a with the increase of the with the changes of the drought and the increase of temperature that leads to severe water resource management problems for the Colorado River Basin. And in this case, for the Weaver Dam, the water level has been continuously low for many years, since 2000 now. That creates really large water resource management problems. So because of those kind of increasing challenges for engineering applications, for infrastructure, either design new infrastructure to combat, to better be more suitable for the future, or either to analyze existing infrastructure for risk assessment, engineers need to consider the future temperature and precipitation information, specifically for the different locations. One such way to acquire the future temperature or precipitation information is through these global climate models. So the global climate models were developed by the climate scientists. They are those kind of physics-based models. They, as you can see from the left graph here, it separates this Earth into different cells. Within each cell, they model the physical interactions, such as energy balance or atmospheric circulations. But the use of those climate model projections for specific engineering applications are still pretty challenging, is because there is a general gap between the raw resolution climate model projections results and the actual observations. Two graphs on the right here just illustrate the general gap between them. On the left here, we have the global climate model projections, the raw output, where on the right, we have the actual observations, which are more detailed, more localized. And for engineering, that we are actually looking at specific locations for the engineering project, the observations are much more appropriate to use. In this case, the global climate model projection might not be appropriate to use for a specific locations. So in terms of the main objectives of this work, essentially they're just to provide a different alternative in terms of global climate models. We look at specific locations. If the engineering applications are a specific location, can we just look at the historic data at that specific locations? And if we can see if we can actually provide the forecast based on the historic data for that specific locations. Then the second kind of objective is to kind of also incorporate the global climate model climate model future climate change scenario from the global climate models to those statistical forecasts. That leads to this kind of two objectives. First, the purely statistical forecast, purely based on historical data, purely based on statistical analysis. And second is kind of a hybrid incorporation of the climate model climate change signal to the statistical forecast. So to start with, what kind of historic data what do we have? So this is not really essentially main focus of this talk, but we have compiled the historic data for the individual cities for about 200 US cities. And we have records start somewhere around 1870 to 2020. So essentially we have about 150 years record for individual cities. And we'll analyze the historic data. What the historic data suggests is that they did exhibit really strong temporal correlation. By temporal correlation, I mean, there is really long-term 10-year decadal, 10-year, 20-year cold and warm periods. And that can be really important if we want to make forecasts based on historic data. The second is that some of the climate variable series, such as precipitation, especially, they exhibit a strong skew distribution that can be important for the use of the techniques as well. Based on those, we essentially ended up to use this autoregressive integrated moving average model, the REopt model. A REopt model, in a way, is still a pretty linear model. It has some consideration of the temporal correlation, or can be considered with the skew distribution that we discussed earlier, with the three terms, the autoregressive, differencing, and moving average terms. It's a little bit more complicated than some other more straightforward method like a linear trend, but a REopt model is also more easier to interpret it than some other more sophisticated machine learning models. And we really want to focus on this model to have more results that are easily interpreted and also can have probabilistic in nature. And they have been used in some forecasting of hydrological time series or forecasting of some other climate variables. To understand how the REopt model works, I have kind of a quick walkthrough of this model. It's relatively simple. So they have three terms, the autoregressive, differencing, and moving edge terms. In this case, we have the REMA 111 model, which refers to those three terms or first order. I have the one example here with the each of the black dots as historic observations up to 2019, up to YT-1, and we have already have the REMA fitting, historic fitting up to 2019. Here, we try to forecasting the values for the year of 2020. Based on the equation, essentially is just the first is the same value from the previous year. Then we add a drift term, the plus constant C here. Essentially, this is the underlying historic climate change trend. In this case, it's relatively small, so it doesn't really change that much. Then we have the autoregressive term. Essentially, is the difference between the previous 2 points times a coefficient. And if you add that up, you kind of shift the values to go down a little bit. Then we finally have the moving average term. The moving average term essentially is just the errors from the previous point. In this case, the epsilon t-1 times the coefficient. Then we add it up. Together. Then we have actually the point forecast for year 2020. So the REMA model is just relatively straightforward. And finally, we have in the equation we have the epsilon t, which essentially is the white noise we assume for these projections here to consider the additional uncertainties for the forecast. And if we follow this process for each year ahead, we can acquire those point forecasts starting from 2020 to 2024. And with the consider of the noise, we can also consider calculate the such as the 80% prediction intervals in this case. And here is just one quick example of how the REMA model works. And this another example here is actually our REMA forecast for an actual kind of variable series. Here we have the annual average temperature in Phoenix. Each black dot here shows the historic observations of the annual average temperature in Phoenix. We have the model fitting as a red line here. In this case, the forecast starting from 1960, 20-year forecasts were made. Then the red dots are the new observations for evaluations. They were not really used for the fitting. So here are the results up to starting from 1960. Then if we update the forecast 20 years afterwards, and starting 1990, 2010, and starting from 2020, you can see how the forecast evolved with the different historic data. And it can be improved with additional historic data. Essentially, the characteristics of the forecasts are that the average level, projected level, or forecast level are similar to the most recent historic level, and you also carry out those kind of long-term historic trend to forecast in the future period. And this is just a forecast for the annual average temperatures to further facilitate the engineering applications that sometimes use daily resolutions. We kind of develop these techniques to kind of have ability to run the daily simulations. The essential idea is still pretty straightforward. We randomly sample the residuals from the daily data, then add it back to the forecast in the annual indices. So here is a comparison between the daily observations and the daily future simulations for the daily temperature in Phoenix. As you can see, there's not that much difference between the observations and the future simulations if we look at the daily resolutions. But if we aggregate the daily data into annual scales, as you can see, this is for the annual average temperature, the future simulated series can still carry out those kind of long-term projected forecasted trend when the daily simulations were aggregated to the annual scales. And if we want to run the simulations for a couple of times, as you can see, those aggregate annual temperatures from those different daily simulations can have this kind of envelopes indicating the possible future uncertainties in terms of the possible future climate change trend. And that is the kind of the idea of the REMA forecast. Essentially, it's a first objective, purely based on historical data, purely based on statistic techniques. But one of the major limitations of those statistical techniques is that it's purely based on historical data. It doesn't really follow the physics. It's not like the global climate models that actually project the future temperature precipitation based on some physics boundary conditions based on the future greenhouse gas concentrations. So what we're trying to do here is trying to bring those two different approaches together. We believe that the statistical techniques are still useful in terms of analyze the location-specific temperature series or precipitation series. You analyze the specific climate variability exhibit in those location-specific series. And also global climate models are useful in terms of bringing the global climate model projected future trend to the forecasts, to the projections. So we then developed this kind of hybrid global climate model or Raymond model. The idea is still relatively straightforward. I have one example here illustrate how this model works. So first we have the annual average temperature in Pittsburgh here. Is the annual average of daily Tmax here as a historic observation, which are the dots, and the black line showing the 10-year moving average. Then we have the individual lighter red and blue lines as the individual global climate model projections, and the bold lines here shows the average or the median projections from those different models. As you can see, because the global climate models are in low resolutions, there's a large difference between the observations and the average projections from the climate models. So essentially, the idea here first is to calculate the difference between the observations and the average global climate model projection results, in this case, into another time series. This is where we bring in the Raymond model. So previously, we forecasting the time series based on purely historic data using a Raymond model. In this case, we're actually forecasting the difference between the observations and the average global climate model projections. As you can see in the third graph here, is the projections of the differences between the observations and the GCM average GCM projections, or the GCM signal in this case. Then we added this projections of the difference to the global climate model projections in the future. And then when certainly, we of course added the data simulation results from the previous techniques that we discussed to this forecasting here. Then we can simulate the future projected temperature series with the two different emission scenarios, as the red and the higher emission scenarios, and blue as the lower emission scenarios, to project the future temperature changes for Pittsburgh in this case. So in terms of the merits of this model, essentially the merits comes from the use of the statistical techniques. The statistical techniques has better assessment in terms of what happens in the past for the location specific, for the locations of the study of the interest, or for the study or the engineering project is located. They have kind of reduced the bias in terms of the future model projections, and it has also better incorporation of the existed historic variability and the long-term historic trend. In this case, by the comparison between the hybrid models and our GCM downscaling products, the hybrid GCM RMA projections seems to be better incorporate the historic trend and the historical variability. So in summary, we believe that the historic data, location-specific historic data, are pretty useful, provide really useful information for engineers, specifically engineering projects that were focused on particular locations. And the existing historic variability and historic trend can be analyzed using statistic techniques, and this kind of analysis can be further incorporated to provide the future forecasts, either purely based on the historic data or to incorporate with the global climate models to project the future temperature observation for the location-specific temperature and precipitation series to facilitate some practical applications such as engineering and adaptation to climate change. And finally, those two models were publicly available. And with that, I want to thank my advisor for providing fundings during my PhD. And with that, I can take any questions. Thank you so much for listening.
Thank you, Yuchuan. Very good. So, can you hear me?
Yes. Thank you.
Yes. Okay, very good. So, I guess when I'm thinking about predictions, I try and find counterexamples to make it difficult. So let's say that this previous year that were the emissions down from previous years. I'm wondering, because the economy was slowed and so forth.
Yeah.
How do you think your model would handle some situation like that, and what would it predict in the future?
So yeah, one thing that I want to mention about this model is that it's not trying to predict what's going to happen next year. It's actually trying to kind of predict the average levels. That's essentially also depends on the objective of this work is to kind of see what's the average temperatures for the next 10 years, or the underlying trend. It's not really developed to predict like exactly the temperature for the next year given by the past year. Is the average expect level, in a sense that the NOAA provides the climate normal for the past 30 years. Essentially, it's try to project what are the climate normals, what the expectations of temperature for the next 10 years or 20 years, not necessarily the next temperature of next year, because there is strong variability of the temperature or climate. Sometimes the effects by the El Nino, it can be really hot next year, or it can be really cold next year. The model itself is just to kind of project the average level, in a sense, the climate normal. So there are some models developed by NOAA try to project the like next year of the climate, but it's not the focus of this model. Great question, though. Thank you.
Yeah. Priya, do you want to ask?
We're getting a bunch into the chat, so I'm just going to go ahead and start with the first audience one. So the first one is from Michael Craig, who says, "Great presentation and beautiful slides." And he says he's still trying to wrap his head around the hybridization, and is asking basically that ARIMA assumes the past trend will continue, but non-stationarity means it won't. So is the idea that the GCM provides the long-term trend and ARIMA fills in the variability around it?
Yes.
So basically, I think just asking for more detail on the hybridization and more intuition for the hybridization.
Yes. So essentially, the idea here is that the climate model projections, in terms of looking at the specific locations, there is a large variations in terms of the actual exhibit historic trend compared to the climate model simulated historic trend. So what this model assumes is that the projected future level still will follow this underlying projected trend from the global climate models, but it does have this kind of variations from that climate trend exhibit in the historic data. So, for example, the year or the average level is projected to increase a little bit higher in the climate models, where the actual historic location-specific time series exhibit less increase of temperature. So the projection is going to be kind of adjust that a bit of balance. It still assumes there will be kind of signal from the climate models. It just considered as a variations from that specific climate change signal from the climate models.
Got it. And so to maybe try to summarize that on my side, the basic idea is that, you're using the GCM for sort of the average notion global climate variables, but then you're looking at like historically there were deviations in different spatial points, for example, with respect to what the climate model was saying. So you're basically trying you are assuming that the distribution of that deviation is similar in the past and in the future. So there's still some kind of stationarity assumption that distribution from the climate model is similar. But then other than that, you're adding it onto the climate model. Yeah, very cool.
All right. I can follow up with another question. It happens to be from Michael Craig as well. So a separate question. Have you done any added value analyses or plan to compare versus other downscaling products, statistical or dynamic? Any comments that this seems useful in power systems context? Yeah. So I did run some analysis in terms of comparison between downscale climate model projections with the results from the techniques that I talked about. But it's a little bit hard to do because to actually evaluate on historic observation, it was limited by the amount of historic data available. And the historic data doesn't really exhibit that much increase. For example, the temperature didn't exhibit that much increase. So if we're looking at the specific 10 years or 20 years, the differences between the downscale projections or the models that I talk about were not that much different in a way, because that the differences were not significant. One way to kind of incorporate this is potentially use the kind of synthetic observation data, perhaps to use use the climate model results as a synthetic observation data to evaluate the actual long-term accuracy. But we haven't done that. And right now, I think main objective or the main merit of this model is perhaps compared to the downscale projections, it does provide some computational efficiency, because the downscale process is quite computational intensive, because you run the downscaling for a whole US, you have really fine resolution cells.
where here is just specifically look at the time series of the location of their study locations and try to provide projections.
Very
Great.
good.
Thank you.
Thank you for your presentation and
Thank you.
Q&A. And I was talking earlier about having a session at the end of this, but I think we're going to be right on time to close everything out. So we're going to move on to the next talk, which is from Vaclav Hasik. Vaclav is a program manager at Building Transparency, as a nonprofit organization behind the EC3 tool and Tally. Vaclav is responsible for quality assurance of data and methodological improvements behind both tools. In his previous roles, Vaclav managed LEED certifications, performed whole building lifecycle assessments, and conducted LCA research in both commercial and academic settings. He's also an active member of the Carbon Leadership Forum and a founder of its San Francisco Bay Area hub. So we can bring Vaclav up. Vaclav, welcome.
Hi, thank you for the introduction.
Yeah, thank you. Appreciate you being here, and we're looking forward to you presenting. So if you can share your screen, great. Very good.
You should be able to see my screen now. So thank you. Thanks again. Let me start with some more background about our organization, Building Transparency, which is a Washington-based nonprofit focused on providing open access data and tools, enabling broad and swift action on climate change effects related to the construction industry. As part of these efforts, our prime service is the mentioned EC3 tool, which is a free and open access tool. It's essentially a tool for finding environmental product declarations and understanding the carbon footprint of products using those declarations. The EC3 tool is also the focus of this presentation, although, as mentioned, we recently took over the further management and development of the Tally tool, which is really a whole building lifecycle assessment tool. We are planning to further integrate the tools because they have very distinct focus, but there's a value in integrating both of them and making both usable to our users. Again, EC3 tool is the focus of this presentation. As mentioned, it's a free tool focused on finding and comparing materials and for planning and comparing building projects. The tool is built on top of an open access database of digitized environmental project declarations, which are accessible digitally via an API. Oops. Just to give you a sort of an idea of the user base, we now have over 10,000 registered users. All of that since our public launch in November 2019. Most of these users are designers, architects, engineers. We have owners and developers who also use the tools, and manufacturers who provide the EPDs for comparisons. I would also like to thank to all of our partners. We had over 50 industry partners supporting the tool's early development. And we also have ongoing partnerships that continuously help us expand and enhance the tool and the underlying data. Now, why we focus on climate change and global warming potential specifically, because we know that we have a problem related to the carbon footprint of our human activities, right? The main motivation for EC3 tool is addressing the embodied carbon of buildings in the dark yellow here. And specifically, in the construction sector, because we know that the whole sector is a big part of the problem. Over the past couple of decades, the development of improvements in operational aspects of buildings have really reduced the operational aspects and climate effects of buildings, but we haven't really addressed this this piece of the pie that is related to manufacturing of materials and products. And so Building Transparency is trying to address this topic of embodied carbon, which according to some, to the American Institute of Architects, the embodied emissions related to buildings for new construction between now and 2050 may account for about 50% of the related carbon effects. So that's sort of why our organization is focusing on this issue. In fact, if we look at the impact of manufacturing more broadly, not just in buildings, but across infrastructure projects and other product manufacturing, the share of the carbon impact pie is actually even larger than that for manufacturing. And so we currently have one place to get embodied carbon data, and that is from environmental product declarations. I think most of you here may be familiar with them, so I'll now go over the sort of the details of what an environmental product declaration is. And I want to point out that we know that the system is not perfect right now. We believe that it can be improved, it can be aligned better, the whole system can be better standardized, and there needs to be an increase in the access to the system for both manufacturers and consumers. In our opinion, we see across the industry that there's a big interest in environmental product declarations and using them for making decisions. And so we see this as a building block for creating a platform for transparency and accountability as it relates to product-related climate change effects. We see a big uptake in the amount of product declarations that are being generated across the industry. You can see that on this graph. And so the main goals of EC3 are really to take these, what are right now PDF versions of documents, digitize them and make data more accessible. At the same time, we then have that responsibility of making sure that the data aligns well and that our users are not misusing or misrepresenting what's included in this data. We also need more engagement from some manufacturing sectors. As you can see on this slide, different product categories have different amounts of product-specific EPDs available. And so we are also working on creating a system that is scalable, and we can actually get more engagement from some of these other manufacturing sectors. So now back to the scope of EC3, it's really focused on getting the global warming potential impacts of the product stage, so from raw material extraction to manufacturing. This is what's covered on virtually all EPDs. Some EPDs also include some of the other life cycle stages, but we see that most products and materials have the largest impacts in the manufacturing stage itself. There are obviously exceptions and nuances to that, such as replacement for short lifespan materials, which is something that is typically addressed with whole building life cycle assessment. And so the way that EC3 fits into a building design process or an infrastructure process is really at this later stages where the design is already set in place, and it's more about selecting materials that are low carbon from manufacturers that actually invest in manufacturing practices and lowering the carbon effects at their manufacturing plants. So that's that. We'll move into a quick walkthrough of the tool. We try to make the tool really as simple to use as possible for our designers and developers that use the tool. So typically the first step in finding and comparing materials in the tool would be just selecting the right material category, right? We start with that, and for example, in this case, we select the ready-mix concrete category. The next step is selecting performance criteria, and this is really crucial for being able to compare products that are functionally equivalent, right? So for example, in this case, for concrete, you can select the compressive strength, the type of concrete that it is, standard weight or lightweight. And there are some other specifications you can select from, and you can also select from geographical region. So for example, for concrete products, they typically wouldn't be delivered more than about 50 miles from a particular building project. So this is why having something like a location-specific filter is really useful. So once we select the product criteria and you search for products, you would get a list of all of the product-specific EPDs as well as industry EPDs that fit your criteria. Here we're just looking at the summary diagram of comparing select number of products. In some categories, you can have tens of products listed in the table of results. You can have hundreds or sometimes even thousands of products in the results. So what we can see here is a selection of 6 particular concrete mixes that were selected for direct comparison. You can see those mixes on the right half of the screen with sort of the turquoise colors. And you can also see the uncertainty ranges that are applied on each of those global warming potential values. Let me zoom into the box plot diagram a little bit closer, because I think that will be the most interesting aspect in terms of how, what we do in terms of driving the innovation across manufacturers. So let's look at this diagram a little bit closer. On the right side, again, we have the single environmental product declaration, and the reported value in the PDF version of that document is in the black, the black bar in the middle. The next thing around it is the EC3 applied uncertainty range. So we conduct internal analyses on different product categories, and depending on how specific the data for an EPD is, we apply this default range of uncertainty around that reported value. We also use the product's conservative value, which is really the top portion of this adjusted value, for documenting reductions for building projects. So that's something that our users would be using for documenting reductions. On the left side, we have the category results. And so this is really the collection of results for all of the EPDs that fit that particular performance criteria search that was defined, when we actually first started looking for product-specific EPDs. Some of the parts of the diagram, so we use the 20th and 80th percentiles as sort of the threshold values for what's achievable and what's conservative in terms of this product category. So at the top of this left sidebar, we have the conservative value for the search criteria. We also, above it, we have the Carbon Leadership Forum baseline, which is also sort of a conservative value for that product category. The difference between those two values is that the CLF baseline is a static value set at one point in time, sort of on a broad analysis of the product category. So for example, in this case, we are looking at a 2019 CLF baseline. The conservative value for the search criteria is really a dynamic value, and it changes based on the EPD data that is in our database, and also based on the specific performance criteria that the user selects. And so now back to the uncertainty range for individual products. What do we cover in that uncertainty? We cover supply chain uncertainties, plant uncertainties, product and batch uncertainties, which are really related to the quantities of ingredients and the tolerances around those numbers. The first 4 points on this list are really where the most impact we have on actually manufacturers' engagement and driving the manufacturers in reducing the carbon footprint of their products. The last 2 points are more generic uncertainty points for just LCA methodology in general. I just wanted to point out the supply chain actually is probably the most important part of the uncertainty factors here. And it's larger for industry EPDs than for product-specific EPDs, just by the nature of the specificity of the data. When we show the industry data as a range instead of a single value, it can help persuade manufacturers to develop product-specific EPDs. By first, the manufacturers realize that they have a more specific data than what lands in the industry EPD data. And they can show that they are better than other competitors, and they can set themselves apart. The second point is that they don't have to be concerned with their EPDs revealing that they might be slightly above the industry average, which we see a lot of the times right now. People don't want to show that they're above the average, right? But if we're looking the 80th percentile as sort of the threshold, that is now a little bit more approachable by manufacturers. Once the manufacturers get product-specific EPDs, and we also show them the supply chain uncertainty related just to the background data, it also daylights the fact that the differences between some of the products are not as clear as the EPDs may point them to be, just by the nature of using generic background data sets. So we now have many forward-thinking manufacturers either asking us directly how they can reduce the uncertainties, or they provide us with more specificity for some of the background data that they have for their products. So that was a quick look at finding and comparing EPD data in EC3. We also enable users to assess the carbon footprint of whole projects. Again, this is just focused on A1 through A3 stages. It's set up more as a sort of a spreadsheet where you can enter the material quantities and actually search for products and link those product-specific EPDs to the material quantities. You can then get a set of either spreadsheet exports that you can use for documentation, or you have different types of diagrams that you can use for analysis. For example, in this case, a lead bar chart. We also use Sankey diagrams for showing some of the data. I would say the most important things on here is on the right side, the total impacts of a building. And you can see the range between the high global warming potential materials and the low global warming potential materials just by selecting, different types of products. So this tool is primarily used by designers and owners and developers, but we also have increasingly more interest from municipalities when they are setting their strategic climate action plans. They actually now are pushing to use the EC3 tool for documentation from their teams, but also for actually understanding what's possible in terms of procuring low carbon materials in the current state of the market. We also see increase in policies across the country that address embodied carbon, and we also see different rating systems that also are looking at this, either from whole building LCA perspective or from environmental product declarations. And so really we are, as an organization, we are continuously improving the EC3 tool in terms of adding new categories, working on additional uncertainty ranges, but we also work on just standardizing the EPD reporting process and standardizing some of the background data, which we also have an ongoing project in terms of developing a North American open access LCI dataset. And with that, that's it for my presentation, and I would welcome any questions from anyone. Thanks.
Thank you, Vaclav. Very good. Appreciate your presentation. So I guess we have a couple minutes for questions. Please, anyone, if you want to put them in the chat, we'll get to them. I guess my first one, you had to go over the functionality of products very quickly. I was wondering, can there be multiple functions that a product satisfies, and can the tool look at that idea and satisfy multiple functions?
Yeah, so there's probably different ways to address that, right, across different product categories. For something like concrete, the functional requirements are typically set by the structural engineer. So, right, the functionality would be set just by the specifications of the concrete itself. So, for example, for something like a floor deck versus beams and column elements, those who have different strength requirements, for example. So that's how you would define the functional performance requirements there. In other products, such as, say, window assemblies, again, you would have different performance requirements like the U values that you can also select in the tool. So it really depends on the specific category that you're looking at.
I guess I have a question as well, which is sort of on the data gathering here, which I can imagine is very difficult. So I wanted to ask, I guess, like two related questions. One around sort of how, I guess, scalable is some of the data reporting stuff here. So if I were to, try to build a building in Canada versus in the US, how much, precision would there be kind of given just the existing data in the tool? And then generally, I wanted to ask, given that it seems like some amount of the LCA data, for example, is self-reported, how a tool like this might deal with, incentives that a manufacturer might have to misreport or to underreport in order to, in some sense, promote their own product.
Right. So I think there's two parts to the question, right? One is scalability, and yes, as you mentioned, it's very difficult to, gather and organize all of this data in a digital form because we're dealing with sort of PDF versions right now. We do that process automatically. I mean, we have different scripts of gathering data from the EPDs, but we also have multiple members of our team going over that data and ensuring that it's accurately picked up by our automatic scripts. Right now, or at least for now, we have been focusing on the North American region because there's a limited number of program operators, and so the format of these documents is standardized in maybe 3, 4, 5 different ways. Obviously, it's different for different